Okay, so today the major agenda is basically studying SU2, or to be more precise, not really SU2 so much, SL2, which will also double as SU2 or SO3 for us, in a slightly different way from the way you've already done in your quantum mechanics course. The SU2 generators have the standard commutation relations that you're all familiar with, and I've already done stuff about raising lowering operators and kits, JM kits, and so on. Now, the reason why I'm going to do it slightly differently is twofold. One is because it can be done, and the other, more important one, is the standard method that uses J plus minus J3 and J square, and uses the fact that J square commutes with J plus J3 as well as J plus minus. And J3 has this commutation. This shows that, first of all, because J square commutes with J3, you can have simultaneous eigenstates of J square and J3. And these rules, these two statements, that J square commutes with J plus minus, and J3's commutator with J plus minus is plus minus J plus minus. Or in other words, in the language of the adjoint operation, what you can see is J plus minus are actually eigenstates of the adjoint J3, right? With eigenvalue plus 1 and minus 1 respectively. This tells you that if you have a state Jm, then applying J plus, which are of course eigenstates of J square and J3, then the application of J plus and J minus respectively will raise or lower the M value while keeping the J value intact. And you have used other results like J plus and J minus are adjoints of each other to figure out the normalization of states and stuff like that. Now, today I want to give you a slightly different version of essentially the same thing, but one in which we are not going to assume, number one, we are not going to assume that these operators, the original generators J1, J2, J3, or are Hermitian, or more strictly speaking, the original generators of SU2, IJ1, IJ2, IJ3, are anti-Hermitian. We are not going to make any such statement. Why? Because Hermitianity is something which we deal specifically with when we are dealing with quantum mechanics. There are applications to these algebras beyond quantum mechanics, where the notion of a Hermitian operator may or may not make sense. So this result in particular, the J plus and J minus are adjoints of each other, which follows, of course, from the fact that J1, J2, which is going to be making up J plus and J minus, are actually Hermitian themselves. This result will not be available to us. Also, the fact that there is a J square which commutes with J1, J2, J3, and we are looking for simultaneous eigenstates of J square and J3, we are not going to make much use of that fact. That we could still use even in a general setting, because remember, the moment you have these commutation relations, I'm just using a slightly different notation for these operators simply because that will make it easier for us to generalize this later. And E plus is commutator with E minus is H. This notation is basically in compliance with the notation of general Lie algebras. That's why we are using this. Here we are not going to assume that E plus and E minus are adjoints. By the way, you can easily recognize what these operators would be in an SU2 context, right? How would they be related to these J3, J plus, J minus? What would the relation be? Yes? These operators H and E plus minus are not new operators. They are basically related to these operators. But what exactly is the relationship? it would be even more obvious if you remember what J plus J minus commutator was. Anybody remember what that is?
Twice of J3.
That was twice of J3. So this H that I'm using here basically is like twice of J3. And because H is twice of J3, the commutator of H with E plus and E minus has ended up with an extra factor of 2. Right? Because basically the adjoint J3, this operator whose eigenvalue is J plus minus R, and adjoint H, they're not the same operator. And H is twice at J3. Because it's twice as big an operator, it has twice as big eigenvalues. Plus 2 and minus 2. E plus minus are the same as J plus minus. Okay. So this is a standard notation that people often use, especially in the algebra theory. So if we use this, it will be more easier for you to read other books. And one of the reasons why this is nicer than using J3, J plus minus is that J3, remember, angular momentum theory tells you that J can have eigenvalues, small j, J squared, can have eigenvalues J into J plus 1, and J3 has eigenvalues M. And the basic feature of these eigenvalues are that they have to be either integers or odd half integers. I'm talking of small g and small m, right? Because I'm using H, which is double of J3, basically here the eigenvalues involved will all be integers, right? Yeah, so this is going to be slightly easier to handle than having to worry about integer or odd half integer cases. Okay. Now, do you remember why this Hermitianity of J1, J2, J3 was so important? Exactly where in the theory of using these ladder operators in angular momentum did Hermitianity actually play a role? I'm talking of basic angular momentum theory, quantum mechanics. There, when you derived all these properties of these Jm states, you must have done this, right? So where exactly did you use Hermitianity of the basic operators J1, J2, J3? What part of your argument actually depended on the fact that these were Hermitian? Yes? Okay, first of all, for a given J, can M be arbitrarily large? You fix the value of J, which essentially means you're fixing the eigenvalue for J square. Is it possible for M to be arbitrarily large or arbitrarily small? Yes? Come on, this is trivial, right? This is something which this particular course happens to be an advanced course, but
Should be from minus J to plus J, I think.
I'm not asking for the range. The range comes in as a result of the you have to distinguish between what is the result of your computation, of your derivations that you carry out, and what is the basic idea. One of the first thing is can it be arbitrarily large? The answer is no. How do you know that? The actual values that it takes comes in later. But anyway, that should have been not something which you think. Come on, angular momentum eigenvalues are elementary enough stuff for it to be sort of burned in your brain by now. But I'm not talking of that. I'm talking of how do you know that J3 cannot have arbitrarily high eigenvalues for a given J square eigenvalue? You are right about the values. It can only go from minus j to plus j. But that comes much later in the development of the theory. The first thing is, why do you at all have to have a bound? And that is a crucial step, because you know you have to have a bound. You know that this ladder operation, that j by j plus, raising operation by j plus, and the lowering operation by j minus must come to a halt. In other words, there must be some state which is itself non-zero, but which is killed, or which when j plus or j minus j plus acts on it, it vanishes. That is, the raising operation must stop somewhere. Similarly, the lowering operation must also stop somewhere. All of this is critical in the theory of angular momentum. So, how do you know that it has to stop somewhere? I'm not asking for the result. I know you know the result. I'm asking, how did you arrive at that in the first place? Okay, hint. What is j square? Is j1 square plus j2 square plus j3 square. Can you now tell me why is it impossible for j3 eigenvalue to be arbitrarily large for a given j square eigenvalue?
Conservation of angular momentum, because there's no external perturbation on the system.
No, but wait a minute. I think you're confusing two entirely different things. Conservation says as time evolves, something cannot change, right? But if something
Yes.
already has a huge value for J3 eigenvalue, I'm asking a state with a huge. Remember, these states, if they commute with the Hamiltonian, they would even be stationary states. They don't evolve in time. Their properties don't change. So conservation is not even an issue here. I'm just
If we,
saying,
hello,
yeah.
If we take any of the JM states and take the expectation of J square in all the states, then that has to be greater than or equal to the expectation of J3 square in all the states. So
Why?
it
Okay,
implies
that's
that
great. But why? Why?
because J1, J2 they are Hermitian operators, so the expectation of those operators. So J1 applying on Jm is actually a state, and the expectation of J1 square in all the states is actually the norm of a state. So that has to be greater to 0.
Right. So this thing, you are saying that this thing has to be positive, right?
Yeah, greater or equal to 0.
Or equal to, could be zero, but can never be negative. Why is that? As you
J1
rightly
is
said, that
J1 is
because this J1 dagger is J1,
yeah.
right?
Yes.
So this critical first step in the theory, which is M cannot be arbitrarily large, that there is an upper bound. And there also has to be a lower bound, because the square being bounded means both the upper and the lower side must be bounded. This follows in the standard version of quantum mechanical calculation from the fact that the operators involved are Hermitian. Okay. If J1 and J2 were not Hermitian operators, then J1 square having to have a positive expression value. That will not be not really be necessary. And in fact, here what you are saying is, if you take the J square minus J3 square and take the expression value of that in Jm, then of course is J into J plus 1 minus M square, right? And if M could be arbitrarily large for a certain J, then of course this could end up being negative. But this is also the expression value of J1 square plus J2 square. Despite the fact that Jm are not eigenstates of J1, J2 separately, they are eigenstates of J1 square plus J2 square, rather trivially, with the eigenvalue given by this. And this cannot be negative. And that's why the M has to have an upper bound, has to have a lower bound. Okay, so that's where you start from in ordinary quantum theory, that the raising operation must stop, so must the lowering operation. And these things together with the other properties combine to give you the whole structure, including the form of the states and everything. Now, I'm going to just say that, okay, let's say somebody prevents you from using Hermitianity, or somebody says, okay, I have some operators. In fact, I've been talking of these as brackets or commutators, right? I've been mentioning these objects as commutators. That's basically because their origin primarily, at least for phases, come through quantum mechanics, where we get these things as commutative brackets of operators. But this could even be abstractly theory, where these are just D brackets with the standard properties. Does not have to be a commutative bracket. Okay. So all these results that we are talking about, that would really not work out necessarily. Of course, what we are talking about now is a representation of the Lie algebra on some vector space. So you really are going to talk about operators and matrices which act on that vector space. But in general, those operators or matrices may be acting on some abstract vector space, and there may not be any meaning to the word Hermitian there. By the way, in order for an operator to qualify as Hermitian in a vector space, there has to be one very important structure defined on the vector space. What is that? Hermitianity makes no sense unless a particular mathematical structure is already defined. What is that? This may sort of seem trivial to you, because for the simple reason that thing, especially when you're doing quantum mechanics, that property is already there in the vector space. It's part and parcel of a Hilbert space definition, in fact. But that property may not be in all vector spaces, which is just the inner product. Unless you have an inner product, the notion of a operator being Hermitian makes no sense, right? Hermitian operator is one which can act on either element of an inner product and give you the same result. Whether it acts on the left or on the right, you get the same result. Right? So you need an inner product in order to be able to at all talk of Hermitianity. Now, in an abstract vector space, you may not have an inner product, so you may not be able to talk about Hermitianity. So that's the reason why I'm looking at this slightly different way of doing the thing. But here, instead of Hermitianity, what will actually give us this restriction is finite dimension. So let's say we are going to look for finite dimensional representations of the algebra given by whatever I just wrote down, h comma e plus minus is plus minus 2, e plus minus, and e plus e minus is h. Okay, so if you want a finite dimensional representation, that means the states, so we are looking at eigenstates of h, and these eigenstates of h will form the basis of my representation. That's fine. But because we are looking for finite dimensional representation, then we again know that raising operation must stop somewhere. So there must be a step, must be some highest value of the eigenvalue for h. Let's call it capital lambda. I'm essentially looking for these states. Right? And once I found these states, I will just take a vector space spanned by these, and I will get a representation of the algebra there. So these states essentially give me the basis states for my algebra. And these are eigenstates of h. Now, we expect that at the end of the calculation, we will get results like lambda has to be integer and so on. But right now, we are not using anything that we already know from quantum mechanics. Okay? But we do know that if it's a finite dimensional representation, then the eigenvalue has to stop being raised. So there has to be a state v lambda which L plus will cancel. Okay? Because this is something which we already have learned from quantum mechanics, that if v lambda is a state with eigenvalue small lambda, L plus minus v lambda, when you act upon by h, will actually give you lambda plus minus 2. 2 here, not 1, because of the 2 here. Right? This is something this is again something we have done in quantum mechanics, the same basic idea. So this fact that acting upon an eigenstate v lambda by n plus minus raises the h eigenvalue by 2 or reverse it by 2, that actually follows from these brackets. So for that, you don't need to invoke quantum mechanics in particular. This will happen whenever you have operators which represent this particular Lie bracket idea. So L plus V lambda is 0, that's trivial. And then what happens if I apply L minus on this n times, this V lambda n times? Yes, what will happen quickly? You're taking L minus, applying it n times on V capital lambda, which is the highest weight state. The state for which the eigenvalue is the largest. What happens here? Yes. Tell me, what state is this? Remember, V lambda are eigenstates of H with eigenvalue lambda. If I apply L minus n times on V lambda, what state will I get? This is a trivial question, but I want an answer to this. Quickly, I don't have all day. I'm just hoping I'm still connected because this is such a trivial question that the answer should be immediate. Or is this question?
So the
Yeah.
vacuum state, the lowest possible energy
First of
state.
all, first of all, there is no issue of energy here at all.
I was just
Right?
saying like analogically.
Lowest possible eigenvalue for H. H is not a Hamiltonian by any chance. It's just a standard notation which is used in the algebra theory, capital H. So lowest possible eigenvalue for this. That's what you're saying. Are you saying lowest possible eigenvalue for H?
Because of the finite dimensionality, it has to terminate at some point. So there'll be
Right. So
some
there must be
ends.
some stage will be killed. I agree.
Yeah. So
But my question is how I'm just applying it n times, small n times, right? Any number.
Should be lambda minus 2.
it'll be lambda factorial.
Factorial. Lambda, what was it? There was another answer which came in.
Lambda minus 2. Right?
Lambda minus 2n will be the eigenvalue, right?
Yes, that's right.
So if I write this, would you agree?
With some constant before.
There could be an overall constant, and when we do quantum mechanics, we do have an overall constant because there we insist that all these states are normalized, right? Why do we insist that the states are normalized? Simply because that makes it easier for us to do calculations later on. However, normalization once again is something you must realize it makes sense only if a norm makes sense. So you must have some kind of a definition of the length of a vector for normalization to at least be useful. I'm saying in a general vector space, norm equal to 1 may not even make sense. You may not have a norm, right? So the normalization constants which people use in quantum mechanics, they are used basically because you want them to have length unity according to the standard inner product in quantum mechanics. But this could be in any other case, and so the constant in front frankly could be anything. And what we could very well do is define the state V lambda minus 2n by this. You just say you apply L minus n times on V lambda, V capital lambda. So there is a largest phase state whose eigenvalue is capital lambda. And on which if you apply L minus n times, you're going to get a state with eigenvalue lambda minus 2n, And what you're going to do is call that thing, L minus acting n times on V lambda, you're going to call that thing V lambda minus 2L. Okay? This is a definition of V lambda minus 2L for us. Definition meaning the choice of the constant in front, we have made it 1. Does that make sense? Yes. Does it make sense? Yes or no? No, you have to say either yes or no.
So can you repeat the question?
So what I'm saying is I have a state V lambda. I apply L minus on this once. What I'm going to get definitely is the state with eigenvalue lambda minus 2. Now, if this were quantum mechanics, I would put a constant in front. The job of that constant essentially, remember, a constant in front of an expression of a vector does not change the fact that it's an eigenvector, or does not change the fact that the eigenvalue is a particular value, right? You keep on multiplying the vector by any number, it will still see an eigenvector with the same eigenvalue. The constant that we put in quantum mechanics is basically to ensure that the length of the vector turns out to be 1. That's square root of j minus m into j plus m plus 1. I hope that's familiar to all of you.
Yeah.
Is it? Isn't it?
Yes.
But that factor which you use for j plus or for j minus, you use square root of j plus m into j minus m plus 1. These factors are there because you want to keep them normalized. I don't care about normalization right now. Because first of all, I may be in a space where normalization doesn't even make sense. So what I will do is L minus V lambda is a vector corresponding to eigenvalue lambda minus 2. So it is a multiple of V lambda minus 2 definitely. But I choose that particular vector to be V lambda minus 2. I can always do that, can't I? The eigenvector corresponding to eigenvalue lambda minus 2 is definitely proportional to this. This times some constant. I just choose that constant to be 1 and say, okay, this is my V lambda minus 2. Any other eigenvector with the eigenvalue lambda minus 2 will be some multiple of this. Is this a legitimate thing to do? Similarly, L plus V lambda, L minus V lambda, L minus square V lambda, what would that be? That will be a state with eigenvalue lambda minus 4. I'm going to call that thing. What I get when I apply L minus twice on V lambda, I'm going to call that thing V lambda minus 4. Okay, it's an eigenstate with eigenvalue V lambda minus 4. But of all the eigenstates with the same eigenvalue, I'm choosing 1 and calling that my V lambda minus 4. Every other eigenstate with the same eigenvalue will be a multiple. Is that okay? Yes? No? Again, no response doesn't really help me. It's just going to slow me down. So when I say something like this, basic quantum mechanics. What did I say? I said J plus acting on Jm gives me a state. Which is a J square eigenstate and J3 eigenstate with eigenvalues J and M plus 1, respectively. Well, not really J into J plus 1, but more importantly, J3 eigenvalue of M plus 1. So it's a multiple of whatever state I'm going to call J M plus 1. What multiple? I choose this factor specifically so that this ensures that this state has length 1. But did I have to do that? If I did not want normalization, I could have said J plus acting on J is Jm plus 1. That state is Jm plus 1. Couldn't I have done that? Again, does this make sense? Yes or no?
So, hello. If there is no constant in that case, wouldn't it require a plus, the product of L plus and L minus to be equal to identity? Because the norm has to be, if the norm is
Once again, you are worried too much about the norm. There is no norm. I don't care.
okay.
And even if there's a norm, I don't have to insist that my vectors are normalized, right? Do I? Look,
No,
some things we do for convenience. Normalizing a vector is something which is convenient. There is no absolutely no God-given rule or scientist-given rule that you have to normalize your vectors. Normalization sometimes makes some calculations easier. That is why if we have an inner product, if we have a norm, we actually prefer using normalized case. But we don't really have to, right? So one thing I've learned from day one about eigenvectors, if x is an eigenvector, 3x is also an eigenvector. Right?
yeah.
So if Jm is an eigenvector, any multiple of Jm is also an eigenvector. Right? But when you are talking about angular momentum space, you have to identify one of these infinitely many possibilities as the vector Jm, and anything else with the same eigenvalues will be some multiple of that. The way which we choose that normalization is actually convenience. The factor in front, not normalization. When I say normalization, I'm actually already specifying what that convenience is. But the factor in front that we choose is actually a matter of convenience. There is no God-given rule that it has to be this factor. Okay? But what is there is sometimes normal. If you have a norm, normalization is convenient, so we normalize. But remember, we are not even assuming that L minus and L plus are Hermitian. So that normalization trick that we actually use. Do you remember how you arrive at this factor? How do we get this factor? Yes? This is elementary theory. How did you get this in the first place? It didn't fall from the sky, right? It had to be there from somewhere. By the way, this again is absolutely elementary quantum mechanics. And if you have forgotten this, I would say it's high time that you studied it again. Look, algebra is an advanced course. Even if you don't master that too much, you
So
will
J
survive.
plus, so actually,
Yeah.
so J plus can be written as Jx plus Ijy over something. Square root
And
of
how
J.
does that help?
Because in that case, if you take the product of the norm of this state in the left side, LHS, then that will give us J square minus Jz, and the square root fact, the factor
With what? With what product of which? What with what?
No, the norm of J plus.
Again, norm.
Yes.
So realize that what you do is you take the adjoint of this. So first of all, let's call this C plus. I don't want to commit to the value. And then use the fact that J plus adjoint is J minus, so that when you take the overlap of this ket with this of this bra with this ket, you actually get J minus J plus, which is related to J square and J3 square, right?
Yeah.
J square minus J3 square minus J3.
Yeah.
Yeah, but that's what I'm trying to point out to you is even this first step. Forget taking the inner product. This will not make sense. J plus adjoint doesn't make sense unless you have an inner product. That's something we should be very clear in your mind. Linear vector spaces don't have to come with inner products. And if you don't have an inner product, then this adjoint relationship makes no sense whatsoever. Okay. So in this step, the step which gave you this factor, you actually used the fact that you have an inner product on your space I'm just saying that can we do this without invoking inner products at all? And the answer is you can. And more importantly, but then this whole idea that V lambda, when you apply L minus on n times, gives you some multiple of V lambda minus 2n. What multiple? That's up to your choice. This constant you can choose up to for your convenience. But in this case, you don't have the well, convenience of demanding normalization. Okay. The factor in front, whatever you put in, will not help to normalize the vector, because normalizing even makes no sense in the general vector space. Does this make sense to you now? So if the constant in front could be chosen to be anything, and I have nothing to gain by choosing it to be something complicated like root over L minus, in this case would be L plus 2n into L minus 2n plus 1 and or something like that. If I don't have any advantage to be gained from them, then why don't I just use 1, which is the simplest possibility? I'm just defining E lambda minus 2n here. That's what you have to bear in mind. So I'm saying, okay, I have a set V lambda, I apply L minus on this once. This, whatever I get, this is what I'm going to call L lambda minus 2. Whatever I get when I do this again, I'm going to call V lambda minus 4, and so on. You agree that if I apply L minus on V lambda, I'm going to get a vector? Do you agree to that or not?
Yes, sir, because they're defined to be the operators of the vector space.
It's an operator acting on the vector space. So this is the vector, right? And this vector corresponds to eigenvalues capital lambda minus 2. Is that right?
Yes.
So this particular vector that I get when I apply L minus on V lambda, I'm going to define that to be V lambda minus 2. Any other operator with the same eigenvalue will have to be a multiple of this. Okay. Look, the problem that you are having with this concept is simply that you have confused what is convenient in quantum mechanics and what is absolutely necessary, because you have been so exposed to using this normalization factor in front, you have forgotten essentially why it's there. It is there not because normalization is sacrosanct. It's because I have to choose one factor here, and if I have a factor which simplifies my calculation in some space, I will use it. So there I use normalization. Here I have nothing to normalize, or normalization won't even make sense in general. So what I like to do, I will not bother with that. I will, since there is nothing to do, no advantage to be gained out of some factor which I put in here, I will take the simplest possible factor, which is 1, and use that to define the thing. And if I continue this way, of course, there has to be a lower limit. So there has to be some capital N, such that L minus n V lambda will be, of course, by general definition, this. But when L minus acts on this state, you are going to get Z. Okay? Right? Now, if I apply L plus, okay, now let's see whether you have understood this notion of the factor properly. What happens when I apply L plus on V lambda minus 2?
You still get the null vector. Because
You get
the null vector as you have here.
L plus on V lambda minus 2, not V lambda.
Oh, okay. So then you get V lambda.
You will get V lambda or a multiple of V lambda.
Multiple of V lambda.
And can I make that constant equal to 1 now? Why not? I did make the constant equal to 1 here, right? L minus acting on V lambda, I got the correct eigenvalue. Then I said, okay, let's make the constant in front equal to 1 and define V lambda minus 2 that way. But then why can't I play the same trick with L plus? Yes, quickly. Why can't we do that?
So there is a non-linear commutation between L plus and L minus.
What? Sorry, could you just repeat that? I couldn't really
There is a
get it properly.
there is a non-vanishing commutation between L plus and L minus. So that will play
Yeah,
a role
that's
there.
true. But that is true, and that will play an important role. But the actual point isn't really that. The actual point is something else. The actual point is at this stage, when I defined v lambda minus 2, my choice of v lambda minus 2 was open. I had a choice of what constant to put in front. I chose to put 1. But when I have done that already, I no longer have a free choice left. Already v lambda is I started with some v lambda, applied L minus on that, and now I defined that to be v lambda minus 2. Now when I apply L plus on this, I will definitely get a state with eigenvalue lambda. But now v lambda is already fixed for me. I can no longer redefine my v lambda to say whatever comes after L plus x on it is my v lambda. At this stage, I had a choice as to which one of the eigenvectors I will like, which one of the multiples I'm going to call v lambda minus 2. But I've exhausted that choice here. Once I've made use of this choice, I can no longer have the choice when I'm using L plus. Is that clear? In other words, v lambda is some state. You apply L minus on that, you get some vector. You call that vector v lambda minus 2. But now, when you apply L plus on this v lambda minus 2, you can no longer necessarily call the result v capital lambda because v capital lambda is already well fixed for you. You cannot just change your scale and call that v capital lambda. Of course, the reason in this case will be what you have said, in the sense that this will be, this of course is L plus L minus v lambda. But then this is the commutator of L plus L minus acting on v lambda. Anybody disagree with this? Oh, I've been actually completely messing up the notation so far. Nobody said anything about that. Do you realize what I've messed up completely here from this point? And maybe that's why you were confused. I don't know. It may have been entirely my error. I completely forgot the fact that I was calling them E plus E minus and started calling them L plus L minus. I hope that was not the reason for all this confusion. I don't think so, because you were right about the eigenvalues. So actually I meant E plus E minus. So I should really say, go back to the proper notation. Okay, let me just. So we have H v lambda equals lambda v lambda. We want to find them out. We said there is a capital lambda on which E plus will give you 0. And if you apply E minus n times on v lambda, whatever state you will get, they're going to call that v lambda minus 2n. And there has to be a state, v lambda minus 2 capital N, which will be killed by E minus. Now we are asking E plus E minus acting on v lambda was v lambda minus 2. So the only difference is whatever I was calling L plus L minus was actually E plus E minus. Better. And that's E plus E minus v lambda, that much is fine. Now, is this okay, this step? And if so, why is this okay? Yes, quickly, tell me. Look, you have to speed up a bit. I can speed up a bit by ignoring the fact whether you're understanding or not. But you have to speed up a bit because I have a lot of ground to cover today. Is this step understood or not? If not, say no, that's fine. If any of
Yes, I
you
understand.
you understood this, right?
Yes, sir.
Okay, and what is E plus E minus? This H?
H v lambda.
So this is lambda v lambda. So when E plus x on v lambda sorry again. E plus x on v lambda minus 2. E plus x is on v lambda, of course, that's 0. When E plus x on v lambda minus 2, you get lambda times v lambda. In general, this state v lambda minus 2n, which you got when you applied L minus small n times on v lambda, you apply L plus on that, you are going to get v lambda minus 2n plus 2. The eigenvalue is going to go up, but you will get some multiple. You no longer have a choice over what that multiple will be. So let's call that Rn. And I want to find out what this Rn is. Okay, how will we find this out? Simple. You just apply L plus on this v lambda minus 2n. And that, of course, is L plus L minus on v lambda minus 2n plus 2. Now, is this equal to, is this correct now? Okay, once again, I've just switched to L. I don't know why. Somehow the angular momentum, actually I remember angular momentum theory too much to sort of use this. But would this be correct? This worked here. Will it work here?
Yes, it should.
Really? So how come E plus E minus and the commutator give you the same result?
There's the second term is E minus E plus. So E plus takes it to V lambda minus 2n, and D minus on the state V lambda minus 2n is 0.
Huh? Really? This small n is not capital N, by the way.
Oh, sorry, then I was mistaking it with capital N.
There is an H. Actually, this is what it is, right? Is this correct? Actually, no. This is not correct. This is equal to H, but this is not E plus E minus. This is actually E plus E minus is this, right? That's a trivial statement. That's just the definition of the commutator. But now I know this is E minus E plus H acting on this. Now, what is this going to be? Quickly, when H acts on this, what will come out? Come on. That is trivial. What's less trivial is what happens when this acts on it. When E plus acts on it, what do you get? It's written on top of the screen right now.
So Rn plus 1 V lambda minus
No,
2.
it's Rn or Rn plus 1. Or Rn plus Rn. Is it Rn or Rn plus 1 or something else?
So Rn is
It's
when
not
E
Rn.
plus acts on V lambda minus 2n.
Yeah, so when it acts on this, you get Rn minus 1.
Yes.
This is for n one less, not one more. Right? Lowered less. Remember, n is how many times it's lowered. So this is a higher eigenvalue state, it has been lowered one less. Right?
Yes.
Is that okay? But then E minus acts on the result and lowers the eigenvalue back to the same value. But E minus, we have already said, will not introduce any factors. So that's one. But what does this give us? It gives us a recursion relation. It tells us that Rn equals Okay. Because this factor is Rn. E plus V lambda minus 2n is Rn times V lambda minus 2n plus 2. So what we have got is these factors, we have found a recursion relation between them. Okay. Rest of the calculation you have to worry about. Remember, in this recursion relation, we have not used Hermitianity in any place. We have just used the bracket. The bracket is part and parcel of the Lie algebra. But you already know what R0 is, right? Remember, 0 refers to a state which has not been lowered at all. So it's V capital lambda we are talking about. So when E plus acts on V capital lambda, what do we get?
We get 0 E plus.
Yeah, we get 0. And that's actually 0 into V. You could say into V lambda plus 2. The number that you get R0 is 0. Right? So I think all of you should be able to figure out from here what Rn is. Okay? Yeah?
Yes, sir.
And using the fact that L minus kills the state V lambda minus 2 capital N. So this is capital N now. Small n was any state, a number of loadings. This is the maximum number of loadings which you must have, because of course if you did not have a maximum number for the loadings, you will get an infinite representation. I'm talking about finite dimensional representation. So E minus acting on this, E minus V lambda plus 2n, what will that give you?
That is 0.
You can call this E plus E minus acting on this. That of course is trivial, but that's again E minus E plus. Right? And E minus E plus acting on this will be R capital N times V lambda minus 2n. Is that okay? R capital N when E plus acts, and then another one when E minus acts, but this comes back. So basically what you get out of this is this equation. R small n you have already found out. At least I hope you should be able to find out from here. This is a very trivial thing to solve and find. So once you have found out R small n, substitute R that for R capital N here, and use the fact that R capital N plus lambda minus 2n has to be 0. What you will get is an equation for capital N. That is the number of times you can lower, and the equation will turn out to have two roots. Now, of the two roots, which one will you take?
Lambda.
Why not minus 1?
Because that would mean that lambda minus 2n is greater than lambda. And then E plus lambda we already know is 0.
Or, okay, that's one way of saying it, but a much easier way to say it, I would have thought would be that capital N is the number of times you're lowering, right? The number of times you're doing something can be at least 0, can never be negative. I think
Yes.
that would be a better way to talk about that, because other things could be incidentally correct. But what does this mean? It means that the number of times you can apply the lowering operator on V lambda and still get a non-zero result is lambda. You do it one more time, you're going to get 0. So how many states do you have in a basis? You can lower V capital lambda times. So how many states? By the way, this immediately shows you that capital lambda has to be an integer, right? That's a quantization. Capital lambda is the number of times you're lowering, so it has to be an integer, cannot be anything else. It has to be a non-negative integer. And what's the dimensionality? How many states have you found out this way? Starting from V capital lambda all the way down to V capital lambda minus 2n. You have lowered capital lambda times. How many states?
2 lambda plus 1.
Again, memory will not help. You are using a result which you know, but this is not that result.
Okay, these go in steps of 2. So
Again, going in steps of 2, etc. are important. Once again, the trouble is you're not thinking of the simple logic here. You're thinking of results that you already know, and that's clouding your logical ability. You started with V capital lambda, lowered it capital lambda times. And that's it. If you lower capital lambda times, how many states do you get?
lambda,
So how many states are there in your basis?
lambda.
No. It's lambda plus 1. Remember the original state V capital lambda. After that, you lowered it lambda times, right?
Okay, that state consider lambda plus 1.
So you got lambda, capital lambda states where you use a lowering operator. But there was one more where you did not, which you started from. So if capital lambda is the eigenvalue of the highest base state, then the dimension of representation is capital lambda plus 1. Of course, what the thing that you do, you call lambda 2j or j half of lambda. And therefore, remember, that's the steps of 2 that you were talking about. And therefore, you end up with 2j plus 1 dimension. Same results. It's just that. And also notice that I've got the full algebra. I've told you what E minus does to every step. I've told you what E plus does to every step. I've told you what H does to every state. And because I've told you what E plus, E minus, and H do to every state in the basis, I've actually told you what they do to every state in the vector space, right? Every state in the vector space is some linear combination of these vectors, V1, V2, V lambda minus 2, and so on. So you know exactly what each of these operators do on all of them. Yeah? This essentially is exactly the same result as the theory of angular momentum, except that we have not used Hermitianity of the operator generators. We have just used the fact that the generators are operators. They have a particular community. The abstract E plus E minus have Lie brackets, but the operators that we are talking about, for them, the Lie brackets are represented as commutator brackets. And we have just used the commutator here throughout. Okay. Now, you use commutators all the time in quantum mechanics, but there you have to remember that sometimes in addition to using commutator brackets, you also use other properties which bras and kets might have. Like, for example, the adjoint property. But that there is, by the way, that there is a bra adjoint to a ket. That there is a bra which acts on a ket to give you a real number in a linear fashion. For that, you don't need the inner product. But the reason why you need an inner product is the fact that you are associating a bra with a ket. That association comes from the inner product in the quantum mechanics in the Hilbert space. It does not come from the linear vector space structure. Did you understand what I said right now? Yes? This is again elementary quantum mechanics. By the way, inner product is between what? Is it between a bra and a ket or between two kets?
Two kets.
So when you say this, are these two kets?
No, generally like the two states are kets. So we define the inner
Kets are
product
not
as
kets. Kets are represented by kets. And what is this? Is it a bra which has nothing to do with the ket? Or is it something else? The point is, this is actually inner product of the two kets phi and psi. But because there is an inner product defined, you can say that corresponding to every ket, modulo some mathematical problems, corresponding to every ket, there is a bra and vice versa. Okay? Yeah.
Yes, sir.
The fact that you have a bra for every ket is a result of the fact that you have an inner product. And this bra for a given ket is the adjoint bra. These notions make sense only with the inner product, otherwise they don't. Okay, so now this leaves me very little time to talk about the other thing, which is SU3. So I will just give a very basic introduction to what this is like. Okay, so a very quick thing is elementary particles have properties like spin, something called parity, which you must have heard of, and other properties like mass. Okay. And the whole basic idea behind this theory is that if you have a bunch of different particles with the same spin, same parity, and roughly the same mass, this could have happened by accident, but almost certainly this is happening because there is some kind of symmetry operation which commutes with angular momentum and hence leaves the spin unchanged, which commutes with the parity operations and leaves the parity unchanged. And also, being a symmetry operation, it commutes with the Hamiltonian, so it leaves the Hamiltonian eigenstates, which essentially is the mass for elementary particles, unchanged, right? So basically, the idea is, if you have some kind of internal symmetry made out of operators which commute with these things, spin, parity, and the Hamiltonian is the same as well. It does not change when you do this transformation. Then you will, even if that had been true, then spin would have been exactly the same, parity would have been exactly the same, and mass would have been exactly the same. If it turns out that you get lots of multiplets, experimentally you see lots of multiplets in nature, where particles have the same spin, same parity, and masses which are very close to each other, not exactly the same. So that is what you call approximate symmetry. So you would say the thing is almost a symmetry, but there may be small terms which don't really commute with the Hamiltonian. Okay. Or rather, the Hamiltonian commutes with almost everything that you do, but the Hamiltonian also the piece, small piece which does not commute with your generators of your representation. Are you with me so far?
Yes.
Okay, so a typical example of this in elementary particle physics, one of the most famous examples, is a nucleon. The proton and the neutron, they're very, very similar to each other. Very similar in mass, same spin, they're both spin half, same parity, and very close masses. Of course, they're very different from each other because one is charged, the other is not. And so basically you say there is a symmetry here, but the symmetry is broken by electromagnetic interactions. So this is a symmetry of strong interactions. It's conserved under strong interactions, which are the major part of the proton-neutron interaction. But there is a difference in the two because the symmetry is not exact. Electromagnetism does not respect the symmetry. But things like proton-neutron, so two particles with the same state. The simplest way of, or then you have pi plus, pi 0, pi minus. Three different particles, but in a way you could think of essentially same particle in three different states. That is, the symmetry operation changes one to the other. Just like rotation would change, say, a spin up to a spin down, or some combination of spin up or spin down. This internal symmetry would change a proton into a neutron and vice versa. Similarly, internal symmetry will change this. Or you could have K plus K minus internal symmetry, which will change one to the other. and there's K0, K0 bar. Two neutral kaons, one an antiparticle of the other. Again, some internal symmetry will change one to the other. So these are basically this symmetry, the way you would mathematically depict it, is basically, okay, you have no clue how to depict it to begin with, so you have to guess what kind of structure that internal symmetry would have. And you would start with the simplest possible structure. The simplest possible structure here would be SU2. Because SU2, how would I guess it's SU2? Because I would say, okay, let's look at the kind of multiplets SU2 have. So, is there an internal symmetry operation which changes the proton to a neutron? If there is, what symmetry operation can that be? The simplest possibility is take an SU2 operation in a just the way the spin up changes to spin down, the proton will change to a neutron. But then, if that is the case, how do you explain pi plus 0, pi minus? You would say it's basically the isospin 1. That is, just like spin 1 has 1, 0, minus 1, 3 states, this has pi plus pi 0, pi minus 3 states. Similarly, k plus k minus would be a spin half pair, isospin half pair. This would be another isospin half pair. That is, the isospin operation will change k0 to k0 bar, and vice versa. Isospin operation will change k plus to k minus, vice versa. Isospin operation again will change pi plus first to pi 0, another lowering will change it to pi minus. So basically what we are doing is we are trying to explain the kind of features we see in elementary particle world and trying to explain them by invoking some kind of internal symmetry. I don't even care what that symmetry is. As long as I know what its representation is, I'm happy. And what I'm saying is the simplest symmetry, which will give me structures of this kind, proton and neutron, very similar. So basically 2 states of the same particle in a sense. Pi plus, pi 0, pi minus. 3 states for the same particle. Or, well, same particle is a bit of a stretch, but basically 3 states connected by the symmetry operation. Or a doublet like this, another doublet like this. It sort of hints that the simplest possibility is you have a symmetry which is like SU2. Some things which have representations of all sides. Remember, lambda plus 1 is a dimension of the representation. So, and lambda can be all non-negative integers, which means the dimension it can be all positive integers. So that's isospin for you. I'm of course rushing through this. You cannot just decide that there is an SU2 symmetry just because of this. What you do is you postulate that there is an SU2 symmetry. But if there is, and if there's an isospin operation which actually commutes with the Hamiltonian, which changes, say I minus, you have I plus, I minus, and I0. And I minus changes P to N. And I plus changes N to P. If this really existed, and using the fact that these operators commute with the Hamiltonian, you can actually make many very important predictions about the properties which will happen, things which will happen in reactions involving these particles. And you can experimentally test whether these reactions work out. So when elementary particle physics, you have not done elementary particle physics, either of you, right? Have you?
No, sir.
Well, if you have done, there would be a whole chapter on this, basically. Elementary particle physics would have essentially said how you would relate the possibility of an isospin invariance to actually experimentally measure properties of these reactions or reactions between various of these things. And by checking that these experiments work out, we would then believe that isospin symmetry is a genuine symmetry of nature. Okay, and experiments worked out pretty fine. Isospin symmetry turned out to be a pretty good description of the symmetry of nature. So here, notice that we don't even have to know what is happening in isospin symmetry. All I would know is there's some abstract symmetry which is acting on one particle state to produce another particle state. And that abstract symmetry has certain commutators, certain operators with certain commutators, and we will use them to find out all the properties. Okay. And as I said, just the existence of a triplet or a doublet or will not be enough to really for people to say that okay, there is an isospin symmetry. What you will really need is concrete evidence that say reactions between these doublets, etc., behave exactly the same way as if they were different states of the same particle with generators changing one to the other and these generators commuting with the Hamiltonian. So I'm not going into the details of that. That would be a whole elementary particle physics course. Okay, and I'm not really trying to talk about that. All I am saying is, after some more particles were discovered, people found something else. People found that while it is true that pi plus 0, pi minus are very similar, the pi plus pi 0, it's not 0. It's called pi 0. I don't know why I wrote it as 0. Pi 0 is just a neutral pion, but without a charge. While it's true that pi plus, pi 0, pi minus are very similar, but when other mesons were discovered, people found that k plus k minus, while very similar among themselves, they are not really exactly identical to pi plus, pi 0, pi minus. Or k0, k0 bar, well, these are both neutral kaons, but they are not completely, these are antiparticles of each other, and they're distinct particles. K0 and K0 bar are electrically neutral, but they're antiparticles. These are very close to each other, these are very close to each other, but if you take all of them together, even these are not too far away from being very close to each other. Okay? They are distinct, not as close to each other as pi plus, pi 0, pi minus are, but a pion kaon system, even there, if you stretch it a bit, you would think that, okay, there may be a symmetry which actually changes pions to kaons, but not really as accurate a symmetry as isospin. Isospin is pretty accurate as a symmetry. Although electromagnetism breaks it, electromagnetic effects are much smaller than the strong interaction effects. So isospin really is a very good symmetry. Whereas this new symmetry we are talking about, which are bigger multiplets, that may not turn out to be a very good, very precise symmetry, but it's still rather strange that so many particles end up having same spin, same purity, and close masses. Okay. And so what you would want to do is you would want to have, so this is, for example, this is an isospin 1 state, right? This I is like this J square, J, small g. So, and I3 is plus 1, 0, minus 1, 3 values. That's why you have 3 particles. Here, this is I equal to half. I3 would be plus half or minus half. Just like angular momentum. Same. Why is it just like angular momentum? Because the basic, while the generators may be completely different, may have come from an entirely different source, the commutator brackets of SO2 and the commutator brackets of SO3 are the same. And since this entire theory about the states came essentially out of the commutator brackets, essentially out of the Lie algebra structure, I don't care whether this is actually a rotation. This is not the rotation group. This is an entirely different group. If a set of operations, but behaves the same way. Okay, has the same ultimate results. So, but people saw that you could also have situations like this. These particles, which have different isospins, at least pions and kaons do, they are also pretty similar. So you would want to have a higher symmetry. So for this, you already had generators like this, just like the generators that we talked about. I've just put in a 1 because now we would want to talk about more things. So here the particles are all labeled with H1 eigenvalues, which are the isospin I3 or third component of isospin eigenvalues. And they are changed from one state to other by the action of E1 plus, E1 minus. Just like angular momentum states change. But this is not, isospin is not enough to describe the bigger multiplets. Because why is it not bigger? You might you might argue that after all, isospin has all multiplets of all sizes, right? Because it has representations of all integer dimensions. So why can't I just say pi plus pi 0, pi minus k plus k minus k0, k0 bar? These 7 states actually come from a lambda equal to 6 or j equal to 3, rather I equal to 3, multiplet with 7 states. Why won't I be able to say that? Yes? Any idea? Even if you haven't had an elementary particle physics course before this, from what I've said already, you should be able to tell me why I can't think of them as 7 states in the same isospin multiplet. The basic idea is these are very similar to each other. These are very similar to each other. For that, we have already used the fact that this is an isospin 1, that is a 3-dimensional multiplet. This is an isospin half, that is a 2-dimensional multiplet, and so on. So they definitely have different isospin values. One for these, half for these. So what do you need? You essentially need another. What you need to do is essentially end up with a bigger symmetry with more generators. In particular, you need another operator H2, which must also provide a label which distinguishes these from each other. And you want H2 and H1 to commute. So here we are trying to sort of rediscover SU3. We are trying to follow Gell-Mann's footsteps. He said because we have bigger multiplets, you have states with different isospin which you can collect together and pretend that they are all connected to each other by symmetry operations. When I say pretend, I mean you are actually using a symmetry operation, but these particles are not exactly the same mass. So they're not really connected by an exact symmetry. And this symmetry is a worse symmetry than the isospin symmetry, but still a decent approximate symmetry. So here, what we are doing is we are assuming that particles of different isospin multiplets come together to form a big multiplet. And how do you distinguish this multiplet from this one or this one? In addition to H1 value, you should have another generator which also has a label, which also provides a label. Now, in quantum mechanics, when you say an operator provides a label, you mean you're talking of states with which are eigenstates of that operator. And so if you have two labels coming from two operators, these two operators must have simultaneous eigenstates. And so they have to commute. So H2, H1 is 0. And let's say you assume that there are step operators here as well. So basically you have 6 operators now. And how are these operators related? Simply by this. We take H1 and commute them with E1 plus minus, you are going to get plus minus 2 E1 plus minus. If you take E1 plus and E1 minus, you are going to get H1. Okay. And what about H2? We already know H2 is commuted with H1 is 0. And we could have, one thing we could have said, we want to keep things as simple as possible. Okay. So one thing we could have said that, okay, H2 commutes with H1 and that's it. I have no more operators. I have just this. But if that had been the case, then every isospin multiplet would also have been a multiplet for this, and this H2 would have just added an extra label. There would have been no way of say, so I would still have pi plus, pi 0, pi minus as a multiplet for this, but I would not have any extra. You get my point? That is, H2 will just tell you that pi plus, in addition to having this isospin label, also has another label coming from H2. Each particle will have two labels. One which is an H1 eigenvalue, the other which is an H2 eigenvalue. But other than that, there will be nothing else, right? Because there will be no operation here which will change, say, for example, pi plus into a k plus or a k minus, right? You understand that? Yes or no? Note that the only operators which can change eigenvalues here are E1 plus and E1 minus. They will change the H1 eigenvalue, but if you assume H2 commutes with them, then that's H2 then will be essentially at the same footing as J squared is for SU2, right? Just remember, we had a J squared which commutes with J plus minus. And what does J plus minus do? It does not change the J squared eigenvalue. So all states in the multiplet will have different H1 eigenvalues, the same H2 eigenvalue, right? You understand that? And no would also be good enough.
Yes, sir.
So you need more step operators. These are called step operators or ladder operators or creation annihilation operators, whatever you want to call it. But you will need more step operators which will also change the H2 eigenvalue. So you would essentially want this to happen. Now, if we had time to do the general theory of Lie algebras, we would have actually realized that such operators have to follow from the basic theory. That step operators. So basically, every Lie algebra, every semi-simple Lie algebra, essentially breaks up into lots of SU2s, basically. But there is one more thing. Now that you have 6 operators in your picture, have I written down all possible commutators? Have I?
What about the H1 with E plus or minus 2 and vice, like
Right.
similar?
So we have not done that yet. So in general, I would like to talk about this. Right? Is it clear? I've already talked about the case where you have I equal to 1, J equal to 1, and I equal to 2, J equal to 2. But what about I equal to 1, J equal to 2, as you were saying, or I equal to 2, J equal to 1? I'm not saying that yet. But one thing I want these operators, E1 plus minus and E2 plus minus, to give you different states of the multiplet, which means a given state of a multiplet is an H1, H2 eigenstate. So H1, say, with value small h1, let's say, h2 with this value, let's say small h2. And these step operators have to give you one step from the other. So basically, the step operators, or this is trivial, E1 plus minus changes H1's eigenvalue by 2. By as by 2, reduces by 2, right? E2 plus minus changes H2's eigenvalues either up or down by 2. That's also easy. But this will tell you how E1 plus minus will change H2 eigenvalues, or H1 or E2 plus minus will change H1 eigenvalues. Okay? Right? So basically, because we want that, what we want is you must have this kind of. So these eigenvalues, these operators should essentially have this kind of commutational relation where these numbers AJI, where J stands for whatever is there. I don't know yet, except for 2 of these numbers. By the way, how many such numbers AJI are there?
4.
4. Actually, it should have been 8, right? Because you have 4 step operators, E plus E minus for 1 and E plus E minus for 2. and you have two H's, so it should have been 8. But notice that what I've already used is the fact that if you use plus or if you use minus, the sign just changes. So between plus and minus, the commutator just has the opposite sign. Now, of these four, that's why instead of 8, you actually have 4. Because the pluses, given the pluses, you already know the minuses. You already know out of them these two. Okay. Right?
Sir,
Yeah.
so hi and e plus minus j. So on the right hand side, is the j summed up or?
No, there is no summation.
Okay, so it's just the ej term. Okay.
The jth one gets acted upon by the jth one. J cannot be summed up here. Remember, J is not a dummy index here, so it cannot be a dummy index on the other side.
Yes, that's what I was wondering.
There's no sum. Basically, you are saying that AJI is the amount by which EJ plus changes the HI eigenvalue. Okay? Right? Now, one question. I already said that I assume this, that if, say, HI acting on EJ plus is commutator, let's say it's alpha EJ plus. The number is, of course, plus AGI according to this. Let's call this alpha. Then HI corresponding to EJ minus. We have assumed has, or we have actually taken for granted here that has been minus alpha EJ minus, right? The plus minus sign here tells you that. Clear? If this number is alpha, which means AGI is alpha, then this number is minus alpha. We have already built that into our notation. Is that clear? Which is why I said instead of 8, you have only 4. Did you understand what I'm saying?
Yes.
But can you justify why that has to be the case? Yes? There's one obvious justification which you can come up with immediately from quantum mechanics.
So these E plus and minus are kind of like the raising and lowering operators. So
Yeah, but
they
so
they act only on a specific eigenbasis of the system.
yeah,
So
but how do you know that AJ plus has to raise by exactly as much as AJ minus has to be lower?
I'm just giving an example from quantum mechanics. So
Yeah, but even from quantum mechanics, how do you know that the J plus has to raise exactly as much as J minus lowers? J plus J minus, of course, has those commutations, but couldn't you have J plus with a commutator with 1 and J minus with a commutator where you have it minus 2? There's something preventing that from happening in quantum mechanics, that you cannot even hook up think of operators like this. J3 commutator J minus, say minus 2 J minus. Then they will again be raising or lowering operators, right? They will just raise or lower by different amounts. But there's something in quantum mechanics which immediately prevents that. And that something is really very, very simple. Again, absolutely elementary quantum mechanics. In quantum mechanics, J plus and J minus are actually adjoints, right? Yes or no? You can see how that's relevant here. What's A comma B commutators adjoint? What is this? Is it A adjoins commutator with B adjoint at all? Yes. Again, if you don't know the answer, you should actually know the answer. These are
Shouldn't it
absolutely
be a
joint comma I
min
Hmm?
a
Really?
minus sign in front?
Yeah, there'll be a minus sign in front.
Yeah.
And that actually tells you that the moment you know J3 J plus commutator, you know J3 dagger J minus dagger commutator, J plus dagger commutator, right? And this minus sign is an immediate consequence of this figure. J3's adjoint is J3 itself, J plus is adjoint is J minus. Because J plus and J minus are adjoints, you have no way of having anything other than a minus sign here. Clear? If
Yes,
this
sir.
had been 2, this would have been minus 2. Absolutely trivial property of adjoints and commutator brackets of adjoints. But what I'm going to claim is you don't even have to use this argument. You would still be able to establish this from the basic properties of a lead bracket, which is this. First of all, what is this? How much is this?
0.
But HI is this. I goes upstairs. You agree?
Yes.
How does that help? Well, whenever you have a double bracket like this, one of the first things you do is rewrite this as right.
Yes, sir.
And now, if I've already assumed this, right? HI comma HI plus is alpha HI plus. Okay. And let's say I don't assume this is minus alpha, let's say it's beta. Then let's see what this tells us. How much is this?
So it's beta
Minus
beta
minus
minus
beta.
It's minus
uh,
beta, right? This is beta, EJ minus. This will be minus
Yes, the
beta, EJ minus.
net
So
thing
this
would be
minus
beta
will go
plus
away.
alpha.
So you get beta EJ plus J minus. And this will
Minus
actually give
alpha
you,
EJ minus EJ plus.
no, not minus alpha, it will give you plus alpha.
Actually, it should be minus alpha EJ minus EJ plus, and then you rotate.
Yeah, the EJ minus EJ plus will be minus this, right? Yeah, right. And this is HJ. So this result is beta plus alpha into HJ. And HJ cannot be 0. After all, we assume that there is an HJ, non-zero generator, which operator which has non-trivial levels. So beta plus alpha has to be 0. Okay. So if this is alpha, the other one has to be minus alpha. Consequence of the Jacobi identity. You don't really need adjoint or anything for this. Adjoints make it easier to actually write down, but you don't need them. Okay. So now, what do? You already have HI. So what generators do you have? You have HI, EJ. So H1, E1 plus minus, H2, E2 plus minus, 6 generators. And if we can think of commutators, so we have already found out commutators which is H1, between this already done. HI, EJ plus minus, we have proposed is this kind. Well, I'm still saying proposed simply because I don't yet know the value of A12 and A21. But apart from that, I know A22 and A11 at least. So what are the other commutators that you can think about? Remember, if you are building up a Lie algebra, then it has to be closed under Lie brackets, right? So if I take a Lie bracket, find something new, then I have to keep on continuing and take brackets with this until I run out of anything new to come up. So what are the other Lie brackets are there?
We can have EJ and EI commutators.
So you can have things like E1 plus E2 plus. Okay, right? Which we have not seen so far. So let's try to all do both of them together. Define this to be E theta plus 9. There's another possibility. These are actually how many combinations are these? When I say commutators, how many commutators are we talking about here?
So the plus or minus is with respect to the outer plus or minus, or the operators plus or minus? I couldn't.
So this, which one? This plus minus.
No, we have defined it as E theta plus or minus. So that
So
plus
E
or
theta
minus.
plus. E theta plus is plus E1 plus commutator with it. So E theta plus is E1 plus E2 plus. That's it. So I define these two commutators. I just want to explore their structure. Remember, I have to take all possible, and apart from this, you also have these. E1 minus with E2 plus, right? So E theta plus minus and E theta bar plus minus. Two new. So we have 4 new generators already. Okay. Right? I've just named possible commutators which we have not talked about yet. Yeah. Apart from this, do you have anything else?
No.
Well, actually you do, because if E theta plus minus turns out to be something new, not a combination of H1, E1 plus minus, H2, E2 plus minus, then I will then have to take E theta plus minus as commutative with all of them. Okay. Yeah, I already have 6 operators here. Now I have invented 2 and 2 more. So by taking commuters, I found 4 more. So it's already 10. If I somehow can show that these are actually linear combinations of these, then I'm happy. Then I don't have anything new to play with. But if we don't, then we have new generators and you have to worry about their brackets. And then if those brackets are also new generators, then you have to worry about their brackets and so on. Okay? Do you understand? So this can get quite messy and it can become a huge thing.
Sir?
I already had 6. Yeah. Anything else?
So is there any handle on which we can like figure out
The
how many
handle
times we take a
basically is,
commutator?
okay, look, the handle is right now, unless you have a guide from, remember here we have just said 2 labels, what kind of operators you can have. And the answer is there are infinitely many Lie algebras which will fit this. Okay. And the things can keep on getting bigger and bigger and bigger. Now the general theory of Lie algebras gives us a way of classifying these, but we are not going to do that right now. What we are going to use is simplicity. Okay, the basic idea is keep things as simple as possible. We had to notice that when we said, we could have started by saying just 3 operators, H1, E1 plus, E1 minus. Why did we have to go in for more? Because experiments showed that there are multiplets where different isospin values, value particles also very close to each other. So we at least had to have one more label for which I had a new operator. And because I did not want that to be just a label which sits around, you would want to have ways of changing one to the other. I would also need these step operators. So I had to have these 6. Now that we have the 6, we have now commutators between these 6, but not all of them. We have these new commutators. And now our job is to try to come up with a way to minimize the extra number of generators we produce. So one great thing would be if E theta plus minus or E theta bar plus minus turned out to be a linear combination of these, we would be very happy. Yeah. But it will turn out, okay, this is something I'm going to ask you to prove. Suppose if I took HI with E theta plus minus commutator. Question, can you see a way of figuring that out? Based on
Use
what you already
the
know.
Jacobi identity.
Yeah, basically E theta plus minus is a bracket. So this is a double bracket, then use the Jacobi identity. And then inside the Jacobi identity, you get HI's commutator with E1 plus minus or E2 plus minus. Right? And these are things you already know. So ultimately, what will turn out is that you will get this. Okay, this is something you have to check for yourself. Okay. So E theta plus minus, these are also step operators. Just like E1, E2 are. And E theta bar plus minus, if you follow the property, again you will get clear. Okay.
Yes.
Yes, sir.
Now if you then you might start by assuming, okay, let's assume that ether plus minus is nothing new. It's basically alpha into H1, alpha 1 H1 plus alpha 2 H2 plus beta 1 E1 plus. This step is usually omitted from most books, but still beta 2 E2 plus gamma 1 E1 minus plus gamma 2 E2 minus. That is, it's nothing new, it's just a linear combination. And a similar thing for E theta bar as well. You could just make an assumption like that. That these are not new, these are just, okay, not for plus minus, of course. For plus and for minus separate values of alpha 1, alpha 2, and so on. Could make an assumption like this. But it will be very easy to check just by using these commutators. Again, a trivial piece of work to show that this is a possibility only if all the alphas vanish. In other words, E theta plus minus or E theta bar plus minus, these new step operators that you found out, they are either genuine new step operators or they are zero. Okay? Can you see?
So
Okay,
how are they new operators if they still depend on betas and gammas?
No,
Like,
the point is you can only, the only possible way, remember you already know this, right?
yes, sir.
Okay. Now you have to, let's assume that it's like this. And of course, we also assume that HI times E theta plus minus is going to be this, right? Because we already know that has to be. This one we know has to be, okay? Right? Because this is just a consequence of the Jacobi identity. Clear?
Yes, sir.
Now I'm assuming, just to keep life simple, suppose E theta plus were just a linear combination of these. Nothing new. Okay? Then my life would be a lot simple. I don't have to worry about that as a new commutator, right? Or new generator. It would be just a combination of the generators I already have. So my dimensionality of my Lie algebra will not increase. The number of independent generators will not go up. But you can easily show that only when this is consistent, when this result, this combination is consistent with this. Okay, let me just show you one way. Suppose I take HI is commutator, I'm going to take H1's commutator with E theta plus. The moment I do that, what happens here? The H1 goes away, right?
Yes, sir.
H1 of course comes with H1, right? And H1 comes with H2. Yeah?
Yeah. Yes.
So if H1 and H2 commutes, then in this bracket, these terms will not be there. But on the other hand, when you take the bracket, you have to get E theta plus minus times the number. Is it okay?
Yes.
That means that simply that these numbers, these alpha 1, alpha 2 must be 0. Otherwise, you will not get this H1 E theta plus bracket to be a multiple of E theta plus minus. Remember, H1, H2, E1 plus, E2 plus, these are generators of a linear generator, but they are basis vectors on the underlying vector space. So they are linearly independent. So they have to match component by component. So just use that match and you will see that ultimately all of these questions will have to be 0. So either E theta plus is 0 or it's an independent generator. The same goes for E theta bar minus, E theta bar plus minus. So either these are independent generators or they are 0. So now, what would be the simplest possibility? What was the simplest possibility? I want to remember the only handle we have on this calculation is simplicity. We want to explain the structure that we see in the world around us. At least that's what Gelman wanted. And Nishijima, Gelman, and other people along with him. Also explain the multiplex structure you were seeing with as simple a structure as possible. Just using SU2 would not do. That is why we had to extend. But now that we have already got 6 generators, it seems that it's going to get worse because E theta plus minus, E theta bar plus minus, I get 10. And I've already seen that the only way these commutation relations can be consistent with a linear combination is that the operator is 0. So what's the simplest possibility? Yes? Come on, I want to keep life as simple as possible for ourselves, which means smallest number of generators.
Should be 0.
Linear
then.
combination of
The only possible linear combination is 0, by the way,
Mm.
as we have seen. The only possible, these commutators have to be obeyed. And once you impose the commutators, the only possible linear combination is 0. So what's the simplest? E theta plus minus and E theta bar plus minus are both? Yes. Come on. Given the options, what is the simplest possibility? Yes. Come on. This is both are 0.
0.
We would love that because then it would tell us that our algebra is already closed. With these 6 generators, I have got the entire extended thing. Unfortunately, this is impossible because you can, for example, you can show very easily. This is something you will have to show yourself. But it's very easy, just Jacobi identity, that E1 plus commutator with, say, E theta bar minus, sorry, E theta bar plus minus E1 minus its commutator with E theta plus actually happens to be A21 E2 plus. Now E2 plus is not 0. If A21 is not 0, which is something you need, then it's impossible for both of them to be 0, right? If both E theta and E theta bar, all these new operators were all 0, then the left hand side here would have to be 0, right? Clear?
Yes, sir.
Okay, so the best you can do is make one of them means two of them 0. So you can make the simplest choice actually. Both 0 would have sounded very nice, but it's not possible. So make this 0, which means basically you know E1 minus commutes with E2 plus, and E1 plus commutes with E2 minus. Okay. But if you do that, then E theta plus minus will have to be given the status of independent generators. Okay. Right? So how many generators do you have now? Yes. How many generators do you have now?
8 generators.
8 generators. Question is, can I close with this? Of course, you would have to consider questions like this. We already know what these are, right? That's what we worked out. Then what about things like EI plus, EI minus E theta plus? Can you see what that is going to be? When I say can you see, I mean this quite literally. And I'm using the word literally here, not figuratively, but exactly literally. Can you see what this commutator is? So as I said, I'm using the word see very literally. Because you can see it on the board right now, on the screen.
0.
No. If E theta bar plus is assumed to be 0, that's what we assume, then this goes away. This result has to go follow, right? Clear?
Yes, sir.
And EI, similarly, you will find that EI plus E theta minus will also turn out to be something you can easily figure out. Again, not a new generator, thankfully. Okay. Here you got E2 plus. There, sorry, this is not EI plus. This is, sorry, I made a mistake. I got E, this is E1. Similarly, E1 plus E theta minus, you will find that out to be actually E2 minus. Not a new thing. Again, very similar, just use Jacobi identity, you'll get all of that. The only problem is these are the generators we don't have. These are commutators which we haven't calculated yet. E1 plus with E theta plus and E1 minus with E theta minus. Now, if we were to calculate them and get a value for them, some new generator, then the thing will again increase. The best thing would be trying to make them 0. When I say try, how can I make them 0? Well, actually, I can make them 0 simply because I still have the values of A12 and A21 undetermined, right? We know that A11, A22 are both 2. But these two I don't know. In order to make this 0, again Jacobi identity, okay, will be in the next homework sheet, which will be the last one. You will get that you will have to have so basically what we are trying to do is build up the smallest possible set of generators, which will essentially explain the fact that you have larger multiplets. And these 8 generators essentially end up well, not essentially, actually end up being the representation of a very famous algebra. It's called SU3. Well, basically, these are traceless Hermitian P/3 matrices. Basically, that's a defining representation. These operators, of course, not matrices at all, but you can, if you look at the set of all traceless Hermitian 3/3 matrices, you will actually find a realization of this particular algebra. Now, why is that related to SU3? Oh, by the way, how many traceless Hermitian 3/3 matrices can you have? How many? Of course, how many is the answer is infinite. How many independent? What are the diagonal values? How many independent numbers can you have here?
2 independent numbers.
Why 2 independent complex numbers would actually mean 4 numbers?
Oh, yeah.
No, you should not agree with me.
No, because they're traceless. So
No,
okay, it should be real because
because not because of traceless.
Hermitian.
Hermitian.
Because of Hermitian.
Yeah.
Hermitian of matrices are real diagonal elements, right? Tracelessness forces the speed down to 2. And here, whatever you have here, 3 complex numbers. If you know these 3, you know these 3, right? Yeah.
Yes, sir.
So how many independent parameters?
It's 5.
No.
Oh, they're complex numbers. So
There
8.
should be 6.
6 up here.
Oh, okay.
And 2 on the
Including
diagonal.
the diagonal.
2
Yeah.
here.
Then it's 8. Yeah.
So traceless, there are exactly 8 independent traceless Hermitian 3/3 matrices. Just like there are, okay, how many traceless Hermitian 2/2 matrices are there? Independent? Again, how many means how many independent? How many parameters does it take? And this is something which, frankly,
Sigma X, Sigma Y, and Sigma Z. So
you already know a basis, right? That's not the only possible basis, but you know a basis. Sigma X, Sigma Y by Sigma Z. All possible Hermitian matrices. You know this, you know this. Because traceless. So this one, you know this one. That means 1 here and 2 here. 2 because complex. Right? So SU2, traceless Hermitian 2/2 matrices. This time with 3 parameters, you have 3 independent matrices, and that gives you the SU2 algebra. Here you have 8 parameters, 8 independent matrices, but I can even write down the matrices for you. Just for example, you'll know if this is X, this is Y, this will be minus X minus Y. So it will be X into 1, 0, 0, 0, minus 1, 0, 0, 0, 0. That's one possible choice. Then if this is U plus IV, this will be U minus IV. So it will be U into 0, 1, 0, 1, 0, 0, 0, 0, 0. That will be another of the matrices, and so on. Just like how sigma comes out of this. This is the most general possible 2/2 Hermitian traceless matrix. And it works out with X times 0, 1, 1, 0. Well, okay, usually you write this as X minus I, this is X plus I, right? So you have that as 0. So just like sigma matrix come from traceless Hermitian 2 by 2, traceless Hermitian 3 by 3 gives you a new bunch of matrices called the lambda matrices, lambda 1 to lambda 8. These are called the Hellman lambda matrices, just like these are the Pauli sigma matrices. And their algebra is exactly the SU3 that we have just almost discovered. We have not calculated everything, but we have essentially said all the important things that we had to say. And whatever other commutations you need to calculate, you can calculate. But why is this SU3 by the way? After all, doesn't U stand for unitary? And doesn't S stand for unit determinant? Yes. Why SU3? Why do you call this SU3? The answer simply is the exponential I times an traceless Hermitian matrix. What do you get?
A unitary matrix.
Not only unitary, because the matrix is traceless, its exponential is unit determinant.
Ah, yes, that also.
So SU3 is the group with capital S, capital E. It has a special unitary 3 by 3 matrix group. The Lie algebra corresponding to that, basically, remember, everything can be brought up by basically breaking up things into small pieces. So small deviations from the identity is measured by this X. These are the generators of the algebra, and you exponentiate them, you get the group elements. So you call this small SU3 not because of matrices here are unideterminantal or trace or unitary. They are not. The traces are Hermitian, but they're exponentials, which is what the group is, and the Lie algebra inherits the name from the group. The small SU3 is the Lie algebra corresponding to the group of special unitary 3 by 3 matrices. The Lie algebra itself is composed of traceless Hermitian 3 by 3 matrices. Actually, I times traceless Hermitian 3 by 3 matrices, if you really want to be very mathematically precise. Okay?
Yes.
Okay, so this is basically where I will draw the line. I've already gone above time. This, of course, was a bit hurried, and again, if I had already had an elementary particle physics course, it would have been much easier for me to just sort of put the mathematical terms across much faster. And that, if I had enough time, I could have done that anyway. But let's call it quits with this course. But I will prepare videos for the general theory of Lie algebra so that you can see there how whatever we have created sort of by force here. Starting from a small algebra, then adding terms to it and building it up. We could also have found a more elegant common description for all of this, at least for all simple Lie algebras. And this would be one example of a simple Lie algebra which fits into the pattern. So we'll talk about that, but not in this course, because the course has ended. And you have an exam which I still don't know when it will be, but
So regarding the exam, like what was the issue exactly with the?
no, the issue is I think Orko had an interview on that day.
Oh, I see. No, I thought like HEP students asked us to like just swap because they were instructed.
No, they didn't ask us to swap.
Okay.
The Orko who wanted to swap.
Okay. Yes, sir.
Because or not swap, he said that whether I can take his exam in a different day or different time, or can the exam be moved up in time so that he can go to the exam, go to this later. That is. sorry, just stop the recording. This is